Alright, so section 3.2, we did talk about that domain and range, and it kind of leads us into this thing a little bit, and we are going to talk about what a function is. Remember that little weird looking picture that I did the other day? What did I call that thing? I called it a function machine, didn't I? Okay, so that was our function machine. It had a little funnel right here where you dump stuff into, and it's got a funnel down on here on the bottom where things come out of it, right? It's just a little machine. Plug and chug, right? You've heard that expression. I've said that before. So you plug in numbers and you chug out, right? It chugs, right? It does its thing, and then it plops out an answer, right? So what kind of numbers do you put into your function? What do we call those things? It's the domain, right? Okay, so the domain goes into your machine, into your equation, or your function is what we're going to call this. So your domain goes into the function, and what pops out of the function? The range comes out of the function, all right? And this thing right here is your function. So if you think of it that way, and it makes things a little bit easier, okay? So the domain is what goes into it, and the range is what comes out of it. All right, so if you understand that, that helps a little bit figuring this stuff out. You can also look at it as a number line. I'm just going to do a positive y and a positive x. If you're in physics, you've probably done a lot of these before, haven't you? Stuff like this. There's a couple of you in physics. And this would be the domain. Remember, the domain is the x value, right? So this is the x-axis. And we call this the independent variable. Okay, they threw this word out here. I don't know how many times we're going to refer to it. Oh, wow, look at this. I didn't even look at this. Look, you probably don't have your books in front of you. But watch this. Look at page 181. It's a little fancier than my machine. But look at that. There's a function machine right there. See it in blue? Isn't that exciting? I didn't even see that until I just opened the book to it. Alright, now theirs goes kind of sideways, mine goes up and down like this, but there you go. So even the book writes a little function machine in there. Isn't that crazy? I can tell you're thrilled to death with that. Alright, so this is called the independent variable. Now when you take physics, and I taught physics for a lot of years, you graph things. Okay, you do an experiment, you get some data, and you have an independent variable or an independent axis. And if this is independent, what do you think this one up here is called? The dependent, good. Okay, because this one depends on this one, all right? Dependence. Did I spell that right? Yep. All right, so this is the dependent axis or the dependent axis, and this is the independent axis. This is the x, and this is the y. Again, we're not going to really refer to it too much as the independent and the dependent, but it's good for you to know because, like I said, once you take physics, who's in physics in here? Norval, you're in there, right? What's have you talked about that before? Talked about the independent variable. Have you done like a distance time graph? You haven't done any graphing at all in physics? You haven't? Well, maybe you will sometime. Usually you do little. So like if this was like the distance, if I was doing a little experiment, right, and I figured out how far something goes in a certain amount of time, all right. So the distance depends on the time. So if a car is going down the road, what do? You click the clock, right? And it ticks off time. 0 seconds when you start, then 1 second, 2 seconds, 3 seconds, and all on and on. So the time is independent. You really can't change the time. The time just keeps on going, doesn't it? But the distance depends on the time that the thing travels, right? So cars going down the road, the time just keeps clicking in a nice even interval, and the distance depends how far this car travels or whatever the thing is, whatever is traveling. The distance depends, the rocket ship, okay, depends on the time that it takes to get there. And then you have a graph, all right? And you might have a graph that looks something like this. And this graph tells you things, all right? This graph is also considered a function. So all this stuff has to do with functions, all right? So there is a rhyme and a reason to this.
What's the rhyme?
I don't know. That's just an expression. I have no idea what that means, but it just seems like it went with that. All right, let's talk about this. Let's remember I just showed you a line right there. Well, a line could be drawn by a bunch of different ordered pairs. Again, for instance, if I was to graph this, you would say, okay, at 1 second, what was the distance? Maybe that was like 10 meters, and this is 20 meters or something like that. Okay, so at 1 second, it's 10 meters. So this is an actual ordered pair right here, isn't it? Right? So it would be like 1 second to 10 meters. You follow me on that? So each of these points on this line would be an ordered pair. This graph, I said, is called a function. So a function is made up, or a line, a straight line, is made up by a bunch of points. So if I have a bunch of points, I could consider that a function as well. All right, so if I had a whole bunch of points here, and we'll put some numbers in here in just a second. All right, so here's a bunch of points. If I had a bunch of points, I could either consider that a function or it might not be a function. Now, let's talk about whether it's a function or not. If it's a function, let's use our x and y axis. I think this might be helpful. Seems like I'm a little scattered today. I don't have my thoughts all completely together, but hopefully it'll all make sense at the end of this. All right, so let's say I have just a straight line right there. This thing is called a function. I want to show you why it's called a function, because like if I had a point right there, no matter where I go on the x, I'm going to be able to go up and it's going to hit a y point. Would you agree with that? Doesn't matter where I go on the x. I can go way, way, way out here on the x. Eventually, if I extended that line out, I would be able to have a point that lies on that line. Would you agree with that? Is there anywhere on this x that I could not have a y value? What do you think? No? So if we wanted to talk about domain and range, the domain would be all the real numbers and the range would be all the real numbers. Okay, for something like that. All right, so every x has one y value associated with it. You okay with that? So every x, like this x right here, it only has one y value associated with it. It doesn't have two. All right? Does that make any sense at all? Let me think about this. Right. So in order to be a function, every x value has to have only one y value associated with it. If this x had two values associated with it, if it had two y values, then it would not be a function. And you say, well, how in the world can an x have two different y values associated with it? Well, that's a great question. I'm glad you asked it, because I'll answer it right now. Watch this. Now, you may not have seen too many graphs like this. You might have in Algebra 2. But what if you had a graph that looks like this? Okay, and then let's say it keeps on going like that. Anybody seen a graph that looks crazy like that? Okay, let's take a look at this x value right here. So I don't know, x is 2, whatever. How many y values does this have associated with it? Well, right, I could hit the graph at this point right here, correct? And I can also hit the graph where? At this point right here. So that one x value, watch this, it's got two y values associated with it. I don't know what these numbers are. Let's just guess. Let's say it's 2, 5, and this would be what? 2, -2. All right, we're just throwing that in there. So look at this x value. This one x value actually has two y values that goes along with that x. You see it? 2, 5, and 2, -2. This is not a function because one x value can only have how many? One y value associated with it. You follow me on that? In order to be a function. So the pictures, I think, really help. Let's go back to the ordered pairs and put some numbers in here. And let's, yeah, we'll just do this. We'll make it easy. Watch. 1, 2, and we'll do a couple different versions of this. 5, 6, and 7, 8. Look at all the x values here. I've got a 1. Does 1 go to any other number but 2 out of these 4 ordered pairs? Nope, only 1 goes to 2 because there's no other 1s here, is there? All right, so 1 just goes to 2. What about this one, 3 to 4? Are there any other things in here where 3 goes to another number? No. What if, so what, 5, 6, 7, 8? Is that a function right there? Yes, it is, because every x value only goes to one y value. What if I threw another ordered pair in here? Watch this. What if I stuck another ordered pair in here and I called it 1, 3? Now look at all these. Now again, I'm taking a look at all these right here. Now 1 goes to 2, doesn't it? All right? Does 1 go to anything else? Yes, it does. 1 goes with what? 3. So this same x value goes to 2 different y values. Is it allowed to do that to be a function?
No.
It's not. So we would say this is not a function.
How passing
Okay.
the vertical line.
Oh, you're getting ahead of me now. You remember that from Algebra 2, right? Okay, so watch. So 1 goes to 2 and 1 goes to 3. So that's not a function. Now, what if I got rid of this ordered pair and I said, okay, forget that one, that doesn't exist. What about all this stuff right here? Then yes, that is a function. Yes, it is a function. All right? Does that make sense? All right, so if you have two of the same x's, right? So I had a 1 and a 1 earlier, didn't I? If you have two of the same x's going to different y's, then it's not a function. That's hard to remember. I teach this every year, and sometimes I have to think about it a little bit. All right, and that's probably why my thoughts weren't so clear at the beginning. But now I think we've got it. And this really helps right here. For this one, every single x value has only one y value associated with it. Let's take a look at this. Let's do another one, and let's think about this. Oops. What am I doing? Oh, I didn't copy it, I guess. Thought I did. And there we go. Now it's copied. So we got this. We got this. And let's make this red so it all looks the same. Now, what if I had a graph that looks like this? Is that a function?
Yeah.
Now, again, what do? We look for all the x's, right? Do all the x's have only one y associated with it? Yeah, because if I go along here, like this x value right here, how many y's does it have? It's just got that one y value right there. It's only that 1 point. Would you agree? Is there anywhere on the x-axis where I could get two y values? No, there's not anywhere, okay? Look, even right here, it's only, if I go here on the x-axis, it only hits the graph at that 1 point, doesn't it? All right, there's nowhere on here on the x-axis, if I pick a point, it's going to hit the graph at two different points. Do you agree with that? Right here, though, it does. If I pick this x, it hits the graph here and here. If I pick an x here, it hits the graph here and here. All right, so it hits at 2 points. So Tiffany brought up something. Did you hear what she said? The vertical line test. And you guys are familiar with that, right? You did this in Algebra 2. So what we do is this. In order to determine, if you just look at the graph itself, in order to determine if it's a graph, it has to pass the vertical line test. And why does the vertical line test work? Because the vertical line test shows you this. It shows you for that one particular x, if I draw a vertical line, that vertical line should only be able to hit 1 point. Right? Because that one particular x can only have one y value associated with it. But look at this. This vertical line shows if I pick like 2 on the x-axis, the vertical line shows that it hits the graph at two distinct points. Everybody see that? So the vertical line test, if the vertical line test says I should be able to draw a vertical line anywhere on that graph, and that vertical line should only hit the graph at 1 point, all right, in order to be a function. If it's not a function, then the vertical line is going to hit the graph in more than 1 point. Everybody see that? So it's going to hit the graph in more than 1 point, and you can see there, that's very true. What about this one right here? Does this pass the vertical line test? This straight line. Look, I draw a vertical line right here, and I can take this and I can move it to here, right? Does it hit the red graph at only 1 point? Yeah, will it only hit it at 1 point? Yeah, I could extend that red graph as far as I want, and that vertical line right there is only going to still hit it at that 1 point. Do you agree? Is there anywhere that I can put this vertical line on this graph right here where it's going to hit more than 1 point? No, there's nowhere on here. It doesn't matter how far you extend that line out, it's only going to hit once. Would you agree? If we come down to this, same thing here. Look, does it pass the vertical line test? Yes, it does, because look, no matter where I put this vertical line, it's only going to hit that graph, that red graph, at 1 point. All right, there's nowhere where it's going to hit it twice, unless that curve eventually came back on itself or something like that. But it doesn't, because the arrows show that it keeps on pointing out this way and this way. So that is a function. Just by looking at it, you can tell that that's a function. Okay? Let's do another one. And we just finished talking about circles, didn't we? So let's draw a circle. Right? Doesn't have to be centered at the origin. I don't really care where it is. So is that a function?
No.
No, it's not, because if I drew a vertical line, now remember I have to be able to draw a line anywhere, a vertical line anywhere on this graph, and if it hits more than one point, then it's not a function. Some people say, yeah, but what if you drew the vertical line right here?
That would be a tangent.
And it would be a tangent. Very good. Okay, this right here, it only hits a circle at one point, but I should be able to take that vertical line anywhere on this graph, and it should only hit at one point. But look, I just put it right there, and it obviously hits at 2 points, so this is not a function. That's pretty easy. It's really nice when they give you a picture and they say, is this a function or is it not a function? That's really, really simple, because you just apply the vertical line test to it. Does that make sense? Yeah, I think so. All right. Talked about the vertical line test. Let's talk a little bit just about this next part, and we'll be done. Let's go blue this time. What we're going to do is this. Like that first line that we drew. Let's go back to that. Remember that very first one like this? This is in the form of what? Y equals mx plus b. Would you agree with that? Yeah. So let's go down to this. Let's give it some blank space right here. So y equals mx plus b would be a function, wouldn't it? Well, yes, it would be a function. Okay, it would always be a function. Y equals mx plus b. For some reason, all right, and there is a reason. What they do with this, instead of calling this y, what they're going to do now is they're going to, since it's a function, they're going to name it a function, and they're going to write it like this. And you've seen this before. They're going to say f of x. All right, it's not f times x. F is not a variable. F actually kind of stands for the word function. All right, it's f of x, the function of x. And let's put some actual numbers in here for m and for b. Let's just say it's like 3x plus 2. Make it easy. So this confuses students when they first see this a lot, okay? F of x. All it means, it just basically means the same thing as y equals, all right? So we can just, whenever we see f of x, we can think of it as y equals something. So what? Not really. It's just notation, okay? It's just different notation. Now, we are going to do something here in a second, okay? But for this right here, if I said graph this thing right here, it's the same thing as just graphing y equals 3x plus 2, all right? So don't get too confused with this. A lot of people see it, and it looks real funky, and it looks crazy. But that's how we say it. We say f of x. We don't say f times x. We say f of x, all right? F is not a variable, all right? It just means the function of x. Now let's see, why in the world would they do that? Why would they change the notation? I kind of was fine with y equals mx plus b, weren't you? I was fine saying y equals 3x plus 2. Why in the world would they change it to f of x? That's crazy. Well, here's a possibility. Do you remember doing problems like this where it said evaluate? Do you remember this? It said evaluate. I'll use that 3x plus 2 again. 3x plus 2 if x equals, I don't know, negative 2. Do you remember that kind of stuff? You did a ton of that in Algebra 1 and Algebra 2. We did it earlier this year, didn't we? Okay. What if we had stuff like this? What does that mean? Evaluate this thing if x equals negative 2. Well, we take negative 2 and we just substitute it in for this. So it's 3 times negative 2 plus 2. That's negative 6 plus 2, which is negative 4. So if I evaluated this, we come out to negative 4. Well, this is what it would look like if it was a function. Okay, if we wrote it in the function notation, all right? Instead of writing all that stuff out like this, this is what they're going to say. They're going to say, I think they just say find. Let me see. Yeah, I think they just say find. This is what they'll do. Here's your function. I'm going to rewrite it again, all right? So f of x equals 3x plus 2. And this is what they're going to say. Here's the problem. It'll say find f of negative 2. Do you see what they're doing here? It's the exact same thing as that evaluate problem. It's just notation. The looks of it is just different. That's all it is. And what does that mean, f of negative 2? Well, remember up here we substituted. We said x equals negative 2, and we just took negative 2 and we substituted in for that x. It's exactly what we're going to do right here. Do you see how that x was replaced by a negative 2 right here? See it in that notation, right? Instead of f of x, what do we say? F of negative 2. So if we replace this with a negative 2, what are we going to do to this? We're going to put a negative 2 in for that x. It's the same exact problem. It's no different. Working the problem is the exact same thing. So it's 3 times negative 2 plus 2, and we already figured that out, and it's negative 4. It's just the notation is different. That's all it is. And it's a little bit more streamlined. It's a little bit better than saying evaluate this if x equals this. All they do now is say find f of negative 2. So what does that mean? You take the negative 2 and you put it in for the x. Okay? Now sometimes they use more than one function. They might have 2 or 3 functions in a row. Now in order to differentiate between the two functions, like we said f of x was 3x plus 2, they may have a different function, but they're not going to say f of x. They're going to use another letter. And the common, you could use any letter, I guess, but the common letter in math books that they use is the letters G and H, all right? So they may say g of x equals, I don't know, negative 2x minus 4 or something like that. They might have another function that says h of x, which is like, I don't know, 2x minus 1 or something, okay? So these are 3 completely different functions. They're 3 completely different lines that you could draw. But here's what they're going to say. They're going to do something like this. They're going to say find g of negative 1. All right, so here's your 3 functions right here. They're 3 separate functions. They really don't even relate to each other at all. Okay, they're 3 completely, look, we'll even break them up like this. Okay, they're 3 completely different functions. If it says find g of negative 1, where are we going to stick negative 1? Are we going to put it in for this one, or this one? What do you think? The middle one, the g function, right? So what do we have? We got 3 functions. We have an f function, we have a g function, and guess what else? We have a, what? An h function. Good. So what we're going to do, if it says just find g of negative 1, and they give you 3 things up here, 3 different functions, this just tells you which one you're going to put it into. So what would you do? You would go put it into this one right here. So you'd go negative 2 times x. What's my x? What did I replace my x with? A negative 1. And then minus 4. Then you just work that thing out. It's negative 2 minus 4 is negative 6. It just happens to come out to the same thing as this did, but actually it didn't come out to the same thing, did it? That was negative 4, sorry. All right? That's pretty simple, isn't it? What if I asked you to find h of 3? What would you do if I said find h of 3? Put the 3 into the what? To the h function. Do you agree? So it's 2 times 3 minus 1. See, I put that 3 into the x, which is the h function. It's no different than anything we've done before, is it? It's just the notation's different. It just looks different. All right, that's all it is. It's just window dressing. But you're doing the math is the same exact thing. That's 6 minus 1, which is 5. We good? And that's the kind of stuff they're going to do. Now sometimes they're going to do this, because you do have a couple of these questions on the worksheet. What if you had this? I'll just start off real basic, okay? Won't even throw any other numbers in there. We'll just do this. And they're going to say, is this a function or is it not a function? So what's a good way to decide if something is a function or it's not a function? We already know if it's y equals mx plus b, is that a function or not? So if I stuck any numbers in here at all, if I put negative 2x minus 3, is that a function? Yeah, because it's just a regular straight line, isn't it? And all the regular straight lines are functions, okay? But this is not a regular straight line. What's an easy way to determine if something's a function or not? Looking at the what? Looking at the graph. Exactly right. Okay? And you're thinking, all right, well, that's not that easy. How in the world am I supposed to graph this thing? Now, you don't have to graph it perfectly. This is actually kind of easy to graph. But how would I graph this? How do I even know how to graph this? Well, remember back in Algebra 1 when you first learned how to graph? You did these things? Remember this little X and Y chart thing? Whatever you call it. Some teachers call it a T chart. I just call it an X and Y chart. You could throw some numbers in and see what you get, right? Well, you know some numbers you can't put in there. You know the domain, right? You can't put in negative numbers because you can't take the square root of a negative number. But we can put in what? What's the smallest number I can put in there? I can put in a 0, right? We could put in a 1. Now watch, I'm not going to put in a 2 because I'm taking the square root. What's an easy number I can put in there so I can get a nice 4? Right, put a 4 in there, right? What else could I put in here? A 9, right? Why is 4 and 9? Why is that a good choice? Because the square root of 4 is 2. It's a perfect square, right? And then the square root of 9 is 3. Now, could you put a 2, 3, 5, 6, 7? Sure you could. You get decimal numbers. It'll be kind of ugly, right? And I would rather not have to go to the calculator, right? I would just rather do it like this. So how would I graph something like this? What in the world would this thing look like? Well, let's put some numbers in. So if I put a 0 in for this, what's a square root of 0? It's 0. If I put a 1 in for this, what do I get? I get a 1. And on these, we're just going to take the positive version of it, okay? We're not going to go plus or minus on this. What if I put a 4 in there? What's that? It's a 2. Actually, hold on. Let me just see what they do here, because you could put the plus or minus, and that would definitely change whether it's a function or not. I want to see what they say about this, because there's like a... where is it? Just says find the domain range. And it's increasing. You know what? I should really talk to one of the other math teachers, because it all depends if you take the positive or you take the positive and negative. And I have to look at this, because there is a notation that tells you whether you just take the positives or you just take the positive and the negative. But let's just take the positives for right now, okay? So we won't worry about plus or minus. We'll just say the positive. So if we do this, what's this graph look like? 0, 0, right? 1, 2, 3, 4. 1, 2. And then what? 1, 1. Now, if I just graphed those 2 points and that was it, it would look like a nice straight line, wouldn't it? But I got to graph a couple more to see what it's going to look like. So what do I graph now? 4, 2, right? 4, 2 is about right here. Is that a straight line? No. It starts curving up, doesn't it? Now, if I go 9, 2, or 9, 3, 9 would be way out here. 3 would be up here somewhere. Scooch it over. So what's it look like? It's a curve, isn't it? It kind of bends. That should be up a little bit higher, just to give me a nice curve. Anyway, you kind of get the idea. You see that? We'll make that dot real big. Cheat a little bit. What's that? Yeah, but it has to be a curve. It just can't be a slanted line, because it's got to include all of these points in it. Right? It's got to be one smooth curve that includes all of these points. So it couldn't just be a straight line. Because if I did a straight line from here to here, it would go like this, and this wouldn't be in it, right? So you can't go straight line here, straight line here, straight line here, because all the numbers in between. Remember, we didn't pick the numbers in between. But if you would have picked a bunch of numbers between 0 and 1 and 1 and 2 and 2 and 3, you'd find out that they would all line up in a nice perfect curve like this. Okay, I just picked some key numbers just to kind of give you a general idea. So if I graph this, is this a function or is it not a function? What is it? It is a function, absolutely. It is a function, okay? Because it passes the what? The vertical line test. Is there anywhere in here where that vertical line is going to hit more than 1 point? No, there's not. Everybody see that? So yes, that would be a function. So if they give you an equation like they did right here, and they say, is this a function? You're going to have to draw a little sketch of it in order to look at it and decide if it's a function or not. They're not going to give you anything real crazy or difficult, but that's what you want to do. Does that make sense? Okay. Now you should be able to do all of these problems. Now there is one problem. At the very last problem is a little bit tough. I don't know if I want to go through that right now. Maybe I'll give you a chance to work on it and see if you can figure it out. At least attempt it, all right? At least attempt it. And then tomorrow, that'll probably be the first thing you ask about, would be my guess. All right? And I think, oh, there's back 2. Tell you what, just do the front of this, okay? Don't do the back. We'll call the back part B, okay? So just do the front of this worksheet. Don't do the back. We'll teach the stuff that's on the back of it tomorrow. Everybody good? Okay, so just doing the front of that worksheet 3-2.